This morning we'll have our second lecture about graphs, and it's going to be on the topic of some very basic graph algorithms. Okay, so this is going to be kind of a LFOA. Does anybody know what that stands for? It's a lecture full of acronyms. Okay, so let's get started. One of the most basic graph algorithms, there's one called BFS. That stands for breadth first search. There's one called DFS. That stands for depth first search. And the most special cases of AFS, which I guess stands for Andrew File System, but it also stands for arbitrary first search. So this is what we're going to talk about for the first half of the lecture or so. So these are all algorithms. What is the problem that these algorithms are solving? Let's find out. So one of the things we talked about towards the end of the last class is connectivity of graphs and reachability, and that's what these algorithms are concerned with. So they're all graph search algorithms. So let's say you're given a graph, G equals VE. There's some basic things about it that you would like to know. Perhaps you have two vertices S and T, and you want to know if there's a path from S to T or a walk from S to T. Or perhaps you just want to decide, is G a connected graph? Or maybe if it is, or then you're happy. If it's not, you want to identify the connected components of G or count the connected components of G. So all of these problems reduce to this problem, which is what we're going to mostly talk about, which is this task. I give you the graph, I give you one particular vertex S, sometimes called the source, and you want to identify all the nodes reachable from S. Okay, for example, if that's all of the nodes, then it means the graph is connected. And if it's not all of the nodes, it means the graph is not connected. Okay, and if it contains T, then you know that S can reach T, and so forth. And this set of nodes of S is called the connected component of S, containing S. So I'll use this notation a little bit for it. Okay, and this is exactly what this most general algorithm we'll talk about, arbitrary first search, does. It takes as input G and S, and it finds all the vertices connected to S. Now, it actually has a bonus. I mean, it doesn't just solve this problem. It returns to you as an output like an interesting structure. It returns to you a spanning tree of the connected component, and the spanning tree is rooted at S. So what is a spanning tree? A spanning tree of a graph is just of a connected graph is just a subset of the edges, which is a tree, and uses all the vertices. Okay, so it's just a tree on the same set of vertices and using a subset of the edges. Okay, maybe more informally, it's a minimal set of edges that connect up all the vertices of G. So here's a picture. Here's a graph. It's definitely connected. And here's a spanning tree highlighted in yellow. So if you look at it, it's actually a tree. Remember, a tree is a connected set of vertices with no cycles, or with one fewer edge than the number of vertices, etc. And it doesn't have to be unique, the spanning tree in a graph. For example, this is another spanning tree. If you squint at that, you'll see it's also a tree. Okay, so it's just a tree, which is like a subgraph of the given graph. Okay, any questions? All right, so let me tell you about this arbitrary first search algorithm. And it's a little bit funny. If you've never thought about this kind of thing before, you might say, okay, suppose this is the graph, and this is G. Sorry, this is G, the graph, and this vertex in the middle is S, and we want to find all the nodes reachable from S. You're like, well, it's like these ones, obviously, right? It's a task that's quite easy to do with your eyeballs if the graph is like drawn for you, at least if it's drawn in a nice way. But you know, it's not like the computer algorithm gets like a picture of the graph as the input, nor does it have eyeballs. And it's not such an obvious task. It's not so obvious how to do the task when the input looks like, you know, this, which is essentially how, you know, it looks as the input to a computer algorithm. You know, maybe it's in adjacency list format or adjacency matrix format, but basically you're getting this information. So now it's not so easy, right? If I give you this graph and say, okay, tell me all the vertices connected to S, you know, You might be like, well, I can see S is down here. It's connected to U, so that's good. We've got S and U. And U is connected to V maybe, so now maybe I have S, U, and V. And S is also connected to Y, so it's not super easy, right? I mean, somehow it seems you have to sort of explore out the graph from S, and kind of without looking a little bit. And that's exactly what this algorithm AFS will do. Okay, so now I'm actually going to show you like the pseudocode for the algorithm. And let me start by saying this is a comment. It uses some kind of data structure. This is not a class about data structures. It's a class about great theoretical ideas. So we won't get too much into it. But just imagine you have some kind of data structure called a bag. And we're going to put things called tiles into it. And the tiles are going to have the names of vertices written on them. Okay, so you might implement this actually in an algorithm with like an array or something. But let's just think of it as a bag for now. Okay, so this is the algorithm. So let's go through it. The input is a graph G and a starting vertex S. So first thing that happens is we write S on a tile and we put it into the bag. And then the rest of the algorithm is a big loop, a while loop. And it proceeds as long as the bag still has some tiles in it. And the very first thing it does, and this is where the A, the arbitrary, comes in, it just picks some tile out of the bag. Okay, and this is a bit non-deterministic, but for the purpose of this discussion, just you can pick any bad tile you want out. Whatever, the first one that's in your data structure. So you pick it out and it has some vertex name written on it, so let's call that V. And okay, now we hit this if statement. We look to see if V is marked. So the idea in this algorithm is you're going to go through the algorithm and you're going to start marking vertices. Maybe you have like one bit that's supposed to be true or false associated to each vertex in the graph, and they're initially all false or unmarked. And you start marking vertices to mean that they are connected to S. Okay, so at the end, like you say, all the vertices that I marked are ones that are connected to S, and all the unmarked ones are not connected to S. And somehow also the idea is that having a tile in the bag that has W written on it means I need to keep exploring from W. Like there could be some more vertices connected to S via W that I want to keep exploring. Okay, so getting back to the algorithm, you pick out some tile that has let's say the vertex V written on it. So the first thing you do is check if it's unmarked. Okay, if you've already seen it before, if it's already marked, then you just forget about it. You're like, okay, this one we already knew is reachable from S. Otherwise, we mark it. And then we go through all its neighbors and put them into the bag. Okay, a tile with them written on it in the bag. Yes?
When we take out V, does it stay out of the bag?
Yeah, so when you take the tile out of the bag, you look to see if it's marked or not. If it's marked, then you just throw it away. If it's unmarked, you put all its neighbors into the bag and you also throw it away. Okay, so we're going to be studying this algorithm for a lot, so it's a good time for more questions. Well, okay, and in this step, by the way, here is an example where it's kind of convenient if your graph representation is adjacency list. Right, because then to do this step, you have some vertex V, you can just go to the array entry for V and go through the list of neighbors and plunk a copy of them into the bag. Okay. So let's do an example run. Actually, it takes a long time, so I'm not going to do the full run, but hopefully I'll get some of the gist of it. Okay, so here's my graph. It happens to be disconnected. And let's say S is 1. Okay, so I'm going to try to find all the vertices, try and find and mark all the vertices connected to vertex 1. Okay, so let's just look at the algorithm. First step, S is 1 here. We put a tile with 1 written on it into the bag. So there it is. Notice actually S is still not marked yet. That's okay. So then we hit the main loop. The bag is not empty, so we pick an arbitrary tile out of the bag. Well, there's only one tile, so we got to pick this one. Okay, and we check to see if it's marked or not. So far it hasn't been marked, so we mark it. Okay, and I'll put the marks as little check marks by the nodes. Okay, and so that's good, right? It's like established that S is connected to S. It's good. And then we go through all the neighbors of this vertex, which are 2, 5, and 6, and we put a copy of them into the bag. So 2, 5, and 6. Okay, and then we throw 1 away. You can see it's kind of exploring the way you might explore with like this big list of edges and so forth, right? I mean, we started at 1. We said, OK, 1 is marked. Now we got to start exploring from 2, 5, and 6. OK, so let's go on. Now we pick some arbitrary tile from the bag, maybe at 6. And we check to see if it's marked. It's not. So we mark it, and that indicates that 6 is reachable from 1. And now we have to put all the neighbors of 6 into the bag, which is, how many neighbors does 6 have? 4, yeah. 1, 2, 5, and 7. You see, actually, now we have 2 copies of 2 in the bag. That's possible. And we have a copy of 1 in the bag, which we've seen before. That's also possible. OK, so we go back up to the top. The bag is not empty. We pick an arbitrary tile. Maybe it was 7. 7 is not marked, so we mark it, indicating that 1 can reach 7. We put all the neighbors of 7 in the bag, which is 2, 3, and 6. We continue. It's not empty. It's going to take a while for it to empty. We pick an arbitrary tile. Maybe it's 1. Here's the first case where we say, 1. We already explored 1. So that one is marked. We don't have to do anything more with it. So we can just throw it away and keep going. OK, so we pick another tile from the bag, et cetera. I'm not going to run the whole algorithm. It takes a little while to do it on the screen. And I want to save some mystery for later, Any questions about it, though, so at this point? Yeah?
Is it possible to calculate the expected values of the complexity for the average case?
The question is about expected values and average case. Do you mean average case? I mean, what's the... Not that we've talked about randomness yet, but there's no randomness in this experiment. I mean, this is, I'm not picking a random tile here. Not that it matters, but I'm just picking an arbitrary tile. So this is not like in some sense, this is not a fully specified algorithm yet, because I haven't literally told you how I picked this arbitrary tile. For now, I'm just going to say, actually, we're going to reason about it independent of the exact means by which I picked this tile. And at the very end, we're going to specify a couple of different ways you could make this line more explicit. And we'll see that slightly different things happen. OK, so we want to analyze this algorithm. Mainly for correctness, we want to show the following, that when this algorithm halts, the set of marked vertices is exactly the set of vertices reachable from S. That's our main goal with this algorithm. OK, so we have 2 sets here, and we want to show them equal. How do you do that? Usually you show that one is contained in the other, and the other is contained in the first one. So let's first talk about why are the set of marked vertices a subset of the reachable vertices. Why is everything that gets marked reachable? This one, I don't want to belabor the point. I think it's pretty clear, right? I mean, if you look at the algorithm, there's no way, if it starts in S, that you can get out of the connected component of S, because you're always just following edges starting from S. So you can never mark something unreachable from S. I think that's OK. It's OK? So the trickier part is this one, to show that if a vertex is reachable, then it eventually gets marked. OK, that it actually successfully finds all the vertices connected to S. OK, so how are we going to do this? Well, actually, wait a minute. Why does this algorithm even halt? I mean, I started talking about OK, when this algorithm halts, blah, blah, blah. We should first check that it actually halts, right? It's not super obvious, because you have this loop where you take something out of the bag, but then you put some more stuff back in the bag, and then you take stuff out, but you put more stuff back in. Maybe it could just go on forever, and the bag would get fuller and fuller. So we better look at that issue before we try to prove anything else. OK, so why does this algorithm even halt? Here's the algorithm again. So let's make a few observations about it. So the thing that worries you is that you keep putting tiles into the bag. So let's see what happens when we put some tiles into the bag. Whenever we put a bunch of tiles into the bag, it's supposed to be because we just marked some vertex v, like 1 line ago, right here. OK, and every vertex gets marked at most once. You see, because you only mark a vertex if it was previously unmarked. So every vertex gets marked at most once. So therefore, we get to this step that puts stuff in the bag at most number of vertices times. OK, so that's good, because every time we put some stuff in the bag, it's like some finite set of tiles, the neighbors of v. So we put at most n bunches of tiles into the bag, each of which is finite. So the bag will never get more than a finite amount of tiles. But every time you go through the loop, you remove one tile. Okay, so we have an absolute upper bound on the number of tiles that will ever go into the bag, and every step of the loop removes one. So it has to halt. It has to halt. It has to stop after finitely many steps. Any questions about that? It's not like it always goes down, but you know in advance, at most 1 million tiles can never go in, so it's got to eventually halt after 1 million steps. So actually, while we're on the topic, we can be a little bit more smart about this analysis. Let's go back to here when we put in the neighbors of V. How many tiles do we actually put in? We put in degree of V many tiles. Okay, each vertex gets hit once, marked once, and when it does, it puts in degree of V many tiles. So the total number of tiles that ever enter the bag is at most the sum of all the degrees, which is, yes, twice the number of edges. And why is it at most this and not equal to this?
You don't mark every vertex.
Yeah, you might not visit every vertex. You only visit the vertices that get connected to S. Okay, so if it's connected, it will actually equal this. Okay, so therefore it halts after at most 2 times, m, the number of edges, iterations. Any questions? You should have a question. There's a mistake. What is it? Now suppose you have the empty graph, which has 0 edges. Does this thing halt after 0 iterations? Do 0 tiles go into the bag? How many tiles go into the bag in the empty graph? 1. I mean, we forgot about this line right here. That's 1 more tile that goes into the bag. Okay, so that was minus 0.5 points. Okay, but it's basically 2 times E. Okay, so it's order the number of edges. Okay, I don't want to get caught up too much in running time analysis because it's not the main focus for us, but although we'll talk about it somewhat. I mean, I want to get back to the analysis. So, now we know the algorithm halts, the bag will always eventually empty. Let's go back to proving that it's actually doing the correct thing, finding all the vertices connected to S. Now, one thing that will help us actually is to use an observation that came up there. We kind of were interested in this fact. When you put a tile into the bag, some tile W, how did it get there? It got there because one of its neighbors sort of just got marked and put it in there. And it's actually going to kind of be helpful to remember that fact. So, okay, that's except for the initial tile, S, which sort of we put in there at the start. So actually, let's update the algorithm a little bit. Let's make it kind of carry around a little bit more information, and let's record that info on the tile. So instead of just putting W in and be like, okay, W, we're going to explore from you later, let's just write down so that we remember, this means we want to explore from W, but just remember, W got in the bag because we just marked V. We got there from V. Okay, so we're not so far really changing how the algorithm operates. We're just having it record a little bit more information as it goes along. Okay, and just so we have a similar thing for this initial tile, we'll write this bottom sign for how it got there. It got there at the start of the algorithm. Okay, so this was the old algorithm, and in the new algorithm, we're just going to write a little bit more information on hopefully the slide recording thing is okay with this. I'll do it a few more times. We'll write a few more information about where the tile came from. And actually, while we're updating the algorithm to maintain a little bit more information, let's insert one more thing here on this line. Let's also, when we mark V, because we just took out this tile that said explore from V and you got there from P, let's write down separately on a piece of paper the parent of V is P. Okay, so I mean you can think of that as having an array called parents and you fill in the Vth entry to be P. Okay, so just like you're keeping track of the marks, you'll also keep track of this parent information. Okay, so this is where we got to in the original version of the algorithm with 1, 6, and 7 marked, and all these tiles were in the bag. if we had run this algorithm, we would have this more information. Okay, we have the same like destination tiles 252, 2536 in the bag, but now we just remember which vertex put them in that bag originally. And furthermore, I kind of drawn the parent information with some yellow arrows. It kind of tells us or reminds us how we got to 6 when we marked it, and how we got to 7 when we marked it, etc. Okay, so let's suppose that we continued running the algorithm at this point, and we pulled the next 3 tiles like this. Let's say the next one we pulled was 6 goes to 2, this one. Then we would add this parent information. The 2 is the parent of 6. And if we pulled 6 goes to 5 next, we'd add this parent information and mark 5. If we pulled 7 goes to 3 next, we'd mark 3 and add this parent information. And then at that point, we would keep running the algorithm, but for each successive tile that we pulled, 2, 5, 2, or 6, it's already marked. So we would just pull it and throw it out. Okay, so we would pull out a tile and throw it out 4 more times, and then the algorithm would really end with this state. Okay, and you see it was good in the sense that we indeed marked all the vertices connected to S, connected to 1, and didn't mark the ones that are not connected. And because of this parent stuff, we can kind of remember how we actually even got to all these vertices. Any questions? Okay, so that's the algorithm, and now we can finally try to prove the theorem that we care about, which is that every vertex in the connected component gets marked. Okay, so to really prove this, I'm going to really prove it carefully. It's going to be convenient to state the same thing this way. We're going to prove that for all vertices y, if there's a path from S to y of length k, then y gets marked. And you say, why did I stick this parameter k in there? So I can prove it by induction on k. Okay, so what is the base case? The base case is k equals 0. We want to show that all the vertices of distance 0 from S get marked. Well, the only thing at distance 0 from S is S. And it's pretty clear that it gets marked, right? The very first thing that happens in the algorithm, you put S in the bag, you take it back out, and you mark it. So that one is OK. OK, now for the induction step. Let's suppose this is true for some particular k. So basically, everything at distance k from S gets marked, we're assuming. And now we want to look at some vertex at distance k plus 1 from, well, not necessarily distance k plus 1, but for which there exists a path of length k plus 1 from S. So let's say we have some y. There's a path of length k plus 1 from S to y. I think it's relatively clear how you would use the induction hypothesis. You'd say, look, we have this path from S to y of length k plus 1. Let's say x is the second last vertex on the path. So S from x is a length k path. So by the induction hypothesis, the algorithm marks x. And if you look at the algorithm, when x gets marked, you put all of its neighbors into the bag. In particular, y has to be one of its neighbors because it's xy is on a path. So you put x, goes to y in the bag. And then we proved earlier that the bag will eventually get empty, even after 2 times cardinality of e plus 1 many iterations at most. So this tile has to eventually come back out, and then by the algorithm, when you take this tile out, you mark y if it isn't marked already. Okay, so y gets marked, and that's the end of the proof. Any question? All right. Great. So we proved that the set of vertices marked when you run this arbitrary first search algorithm on G starting from S is exactly the set of vertices connected to S. Now, it's very annoying to always say, like, OK, it's going to talk about all the vertices connected to S. So let me just assume from now on that S, the graph is connected, so that this connected component is all the vertices. Otherwise, you can just forget about the other vertices for what we're about to say. Now I want to come to this bonus information that I mentioned a long time ago, which is that not only does AFS, solve the connectivity problem, it actually finds for you this spanning tree of G rooted at S. And how does it find it? It's encoded in this parent information that we kept around. So how can we show that this parent information, which is like those yellow arrows that we drew when we were looking at the picture of how the algorithm runs, how can we show that it actually gives you it is actually a spanning tree? Well, it's certainly a bunch of edges. By the way, when I drew it with the yellow arrows, I kind of thought of them as directed, but we're really still thinking about them as undirected edges. I sort of just drew them in a direction to remind you that this is the parent of that. Okay, so we get a bunch of edges at the end of this algorithm. And each vertex G gets exactly one parent edge, because you get your parent edge when you're marked, and everybody gets marked exactly once. Okay, it depends whether or not you count S. S's parent is this bottom symbol, so let's just say that doesn't count. So every vertex other than G gets exactly one parent edge. So overall, how many edges do you get? You get one for each vertex other than S, which is the cardinality of V minus 1. And that's a good start, right? Because that's the number of edges you're supposed to have in a tree. Number of vertices minus 1. So we have a bunch of edges. It has the right number of them, cardinality of V minus 1. So how do we check that they make a tree? What do we need to further show? Yeah, we need to further show that they're connected, that every vertex can reach every other vertex using just these edges. How are we going to show that? Yeah? Induction. Okay, go on. Oh. Does anybody have another idea? Yeah?
Since everything is reachable from S, just go back to S and then go to that. No.
Yeah, exactly right. So, okay, if you really had to, maybe you would prove this by induction, but I think it's pretty clear that for all vertices V, if you start following their parents backwards, you have to get to S, because, where do these parent edges come from? First S put out all its parent edges, and then they put out parent edges and so forth. So if you eventually have some vertex V that you hit, and you follow the parents back, you get to S. So therefore, any two vertices in the graph could both do a walk along parent edges to get back to S. So therefore, you could do a walk between them, right? You could first go back to S and then go to the other one. So every two vertices in the graph are indeed connected to each other just by these parent edges. There could be a faster way, but this is at least some way. Okay, so the parent edges form a tree because we have the right number of edges and it's connected. Okay. Any questions about that? Okay, so in some sense, that's all I want to say about the general algorithm, AFS. We showed that it has this A in it, this arbitrary part, where you choose an arbitrary vertex out of the bag, but no matter what you do, it's going to correctly find all the vertices connected to S, and it's even going to return you a spanning tree. So now let's talk a little bit about how you would actually implement this with an algorithm. And the first case of this is depth first search, DFS. And that's what you get if you actually implement the bag using a data structure called a stack, which maybe you've seen before. So a stack is like a bag that has the last in, first out process. So it's property. So it's something like this. When you have a tile, you put it onto the stack. And then when you want to get something from the bag or stack, you just take the first thing off the top. Okay? So how would you actually implement this with an array? You have an array and an index pointing to the end, and when you want to add something, you just put it in the array and move your index this way. When you want to take something out, you take the thing off the top and move the pointer back this way. And for the purposes of letting me show a picture, let me assume that the graph is stored in adjacency list format and that the vertices in each list are sorted. So let's say we have this little graph. So what actually happens when you use a stack here? Well, the quick version of it is, you start exploring from 1. You put the tile 1 goes to 2 on the stack, then 1 goes to 5 on the stack, and 1 goes to 6 on the stack. Okay? And then, in the next step, you take the top thing off the stack, which is 1 goes to 6. Thank you. So you go to 6 first. And then the algorithm puts all the neighbors of 6 into the bag or on the stack, which are 1, 2, 5, and 7. So the next thing that is on the top of the stack is 6 going to 7. So the next thing you add is this. And then 7 puts its neighbors, 2, 3, and 6 on top. You take the top one off. That 7 goes to 6. But you've seen 6, so you'll discard that. Might have to watch the video again on this one with a piece of paper. And then the next one is 7 goes to 3. So you take that off, and you mark 3. You put its neighbors on, 2, 6, and just 2 and 7. You discard 7. The next one is 2. Eventually, you'll come all the way back and do 5. OK, so this is called depth-first search because if you look how it works on graphs, it really starts from the source vertex and it goes like all the way sort of out, always following like the last numbered neighbor. So it makes these really long, and then only then does it sort of come back up. So it makes these really long, stringy trees. Now, one cute thing about depth-first search is that if you're writing it in like a high-level programming language as opposed to a Turing machine or something, usually programming languages allow recursion. And how does recursion actually work when it gets compiled down to like Turing machine-like code? The compiler needs to keep track of where you are and like all these function calls, and it uses a stack for that. So actually, the compiler kind of can build a stack for you, which means you can actually implement depth-first search without like writing any data structures yourself. I mean, this is the whole code. To do a recursive depth-first search from V, check if it's marked. If not, mark it, and then do the recursive call from each of the neighbors. OK, so that's actually one cute thing about depth-first search. Any questions? The other well-known instantiation is breadth-first search, which starts with B. And this is the case when the bag is a queue data structure. A queue means like a lineup in UK English. And that's a first in, first out principle. So it's sort of like this. You have like a list, and like when you add something to the list, it goes at the back. And when you take something out, it comes from the front. OK, so probably you would implement that with a linked list or something. And we'll again assume, for the purposes of this picture, that we use the adjacency list representation. So here, what happens, you start with 1, you add the neighbors 2, 5, and 6, and they go in the line, like 2, then 5, then 6. So then you do 2 first. It puts out its neighbors, which are 1, 3, and 6, but they go at the back. So what's left at the front? What comes next? 5, yeah. So you get to 5. It puts out its neighbors, but they go at the back. So you still do 6. Right? So you kind of do all the vertices connected to 1 first, 2, 5, 6. And finally, when you're finished with them, you come to like the neighbors of the first guy you handled, 2. So the next thing will be 3, and then eventually you'll get 7. OK, so it's called breadth-first search because if you look how it works on like a big graph, it kind of makes these wide, bushy trees where it kind of goes all the vertices at distance 1, then all the vertices at distance 2, etc. Any questions about it? It also has this bonus property, which I just mentioned, which is that the vertices get marked in order of increasing distance from S. So you mark all the vertices at distance 1 first, then all the ones at distance 2, etc. I won't prove that. It's a bit clear. You can prove it for yourself as another exercise by induction if you really wanted to. So in particular, if you take the code with breadth-first search, and whenever you're about to record the parent information, you also keep around some distance information, and you say that the distance of this V that I just visited is whatever its parent distance was plus 1, then that'll actually give you all the distance information from S, which is 1 in this case. So you'll start, OK, I didn't say it, but you start by marking 1 as having distance 0, and then these vertices all have distance 1, and then these vertices all have distance 2. Any question about that? Okay. So in fact, this this spanning tree that you get back from breadth first search when you run it on an S is called the shortest path tree because it has all the shortest paths from S to other vertices. It doesn't necessarily give you the shortest paths between any two vertices, but just the shortest paths from S. Let's talk a little bit about the running time while we're here. So here again is the algorithm. And remember we said that the total number of tiles you ever put in the bag is order of E, order of number of edges. And it's actually exactly this if the graph is connected, which is what we'll assume for now. And now we actually have a data structure for this bag. Okay, so either a queue or a stack. And it's not hard to tell that to see that putting something into a stack takes order of 1 time. You just add it to an array. Taking the top thing off the stack is also order 1 time. And similarly for a queue, you just have to hook it up at the beginning or the end of the linked list. So these sort of underspecified things, this pick a tile and put a tile, they just take order 1 time. And now the way you can analyze it is, there's some order 1 time stuff. And basically, it's the presence of a tile in the data structure that causes you to do stuff. And you sort of spend order 1 time per tile. Basically to put it in, take it out, mark its neighbors, and so forth. So as a consequence, the total running time is order of the number of edges, which is actually very good. I mean, you just have to look at each edge constant number of times, do a constant amount of work for it. Okay. Now one small thing, I mean, this AFS algorithm on G and S just finds the connected component of S. So maybe you run it and you found the connected component of S, but maybe it's not everything. You probably still want to find all the other connected components. So what should you do?
Pick an unmarked vertex and run it again.
Yeah, pick another unmarked vertex and run it again. And repeat this. And it's very short. I mean, if you want to make a big algorithm that finds all the connected components, you just go through all the vertices, check if they're unmarked. If they are, find its connected component that marks a bunch of vertices. It's connected to V, and then you just keep going and do it for all the unmarked vertices. So you can plug in BFS here or DFS here, it doesn't matter. And what is the overall running time? It's definitely going to be order of the number of edges, because each component has a subset of the edges. And you'll have to sort of do O1 work for each of them. So it's order of the overall number of edges. But it's actually not just that, right? Plus the number of vertices. Like if you ran this on the empty graph, it wouldn't take 0 time, because you still have to do this loop of going through all the vertices. So it's order of V plus order of E. It's very annoying with graphs because there's 2 parameters, the number of vertices and the number of edges. And so the running times always tend to involve both of them, which is annoying. It's only somewhat ridiculous graphs that have fewer edges than vertices. So almost always the number of edges is more than the number of vertices. So you can just work with the number of edges. But technically you can have a nearly empty graph. So you have to worry about that. OK, we talked about why. OK, so we saw AFS, we saw BFS, we saw DFS. Obviously, there's one thing missing, which is CFS. Thank you. Yeah. CFS. So what should that stand for? It's going to stand for cheapest first search. And cheapest first search is another instantiation of this arbitrary first search. But it has a bit of a different motivation. Its goal is not just to find connected components. It's to find a minimum spanning tree of the graph. And let's say, what does that mean? I mean, every spanning tree is going to have n minus 1 edges. So what does it mean, minimum? Well, it refers to more general graphs where the edges have costs. So let's talk a little bit about this definition of weighted graphs. So often in life, you have not just a graph, but each edge has some real number associated to it. Okay, so maybe this is a graph, and it has some real number written on each edge. And this real number is often called various things, depending on the exact, application it came from. But these generally all mean the same thing, like weight, length, distance, cost. It's some like price for the edge. Okay, we'll probably mostly say cost. Okay, and so you can think of it formally, a cost function is it's a mapping from each edge to the real numbers. And we're going to assume that costs always are positive, okay, unless otherwise specified. Mostly, we only consider positive costs. Okay, so before we get to cheapest first search, I want to tell you the story of the problem it's supposed to solve, which is minimum spanning tree, where I promised you there's a lot of acronyms. It's usually called MST. Okay, so we have to go back to the year 1926, and the place, Brno. Does anybody know what country that's in now? Brno? You know geography? No, that's Bern. No? It's in the Czech Republic. And the hero of our story is this person, Borůvka. I think Borůvka means blueberry. Okay, so he was a mathematician. He actually just finished his PhD in like 1923. He was still doing research in Brno. And he had a friend called Saxel who worked for this thing. Can anybody read Czech? Yeah, me neither. It means the West Moravian Power Plant Company. And they were trying to electrify Moravia, like bring electricity to all the towns. And he asked, his mathematician friend, like, what would be the most efficient way to do this? So maybe this is Moravia. I mean, Brno is the biggest city, but there's a bunch of towns. And let's say there's an edge between two towns, if it's like feasible to connect them by power lines. There's no mountains or something. And there's going to be some costs on the edges. So whether that's, the distance, or maybe that's like the amount of money it would take to install power lines along this edge, there's some cost to it. So maybe it's like this. Okay, and what you're trying to figure out, what Saxel wanted to figure out was, we can build power lines between the cities, and we can put the power plant wherever. But we just want to make sure everybody gets electricity. Okay, and so we want to do it in like the cheapest way too. So I think it's like this. You see, we selected some edges, we built some power lines along these edges, and now there's power going to every town. If we put a power plant anywhere, it doesn't matter. Okay, and the cost is the sum of these overall costs. Okay, so more formally, the MST problem is this. You're given a graph G, and it's got a cost on all the edges. This should say E. That's a mistake. And the output, you're supposed to output a subset of the edges that connect all the vertices and have the minimum total cost. Now, why is it called minimum spanning tree? Well, I claim that the minimal cost edges that connects all the vertices will be a tree. Why is that? Yeah?
If it wasn't a tree, it would have a cycle, so like there would be one more edge than you needed, so you'd be spending too much money.
Why?
Because
Yeah, you would have a cycle otherwise. So
maybe not necessarily a cycle, but you'd have
no, you would have a cycle if you have more than a tree and it's connected.
because wait. So what's your question?
Why is why would that not be minimum cost?
So you have a cycle, then you have two ways to get to one vertex. If you have a cycle,
Yeah.
so that's two more paths than you need. You only need one path to each vertex.
Well, I wouldn't quite put it like that, but you can delete one edge on the cycle and you would get a lower cost tree. Yeah. Okay. And that uses actually the fact that all the costs are positive. And it would still be connected. Okay, so that's the minimum spanning tree problem. So here's an example. This is, well, it's the same Moravia graph, but just with letters. And I did the math. This is the minimum spanning tree. That one's in yellow. And it happens to be the unique solution. And the cost is just the sum of the costs, which is 42 in this case. Now I'm going to make a simplifying assumption. I'm going to make an assumption when we're studying the minimum spanning tree, which is that all the edges have distinct costs. And if you make this assumption, it's not hard to show that the minimum spanning tree is actually unique. And that's convenient. It's even just grammatically convenient because you can speak of the minimum spanning tree rather than a minimum spanning tree. Now this assumption is not a big deal. It's without loss of generality by a very simple trick. Maybe it will put on the recitation or something. There's a little trick that shows it's without loss of generality. And in fact, here's a hint for why that's true. This is an actual quote from the actual Boruvka. Whether the distance from Brno to this other city is 50 kilometers or it's 50 kilometers and 1 centimeter is a matter of conjecture. That's supposed to be a little joke, but I mean the point is, probably in real life, if you have costs on your edges or distances on your edges, they're not going to be literally exactly the same. So maybe that's why you wouldn't worry about this assumption anyway. But anyway, you can get around this assumption very easily. But I'll assume it for now. Okay, so let's come all the way back to AFS, which we studied before, this arbitrary first search, and we'll talk about cheapest first search. And this is sometimes called Prim's algorithm because this Texan guy, Prim, published it in 1957 in English. But actually it was discovered a long time ago by Jarnik, who read Boruvka's original paper about MST and wrote him a letter saying, like, I think I have a simpler algorithm. Fortunately for him, it was in Czech, so not many people knew about it. But he figured it out 27 years earlier. And actually, Boruvka's had a different algorithm from 1926. But we're going to study mainly this algorithm due to Jarnik and also Prim, which is cheapest first search. Okay, so this was our AFS algorithm, arbitrary first search, and we're just going to, do the cheapest edge every time we pick out a tile. We'll pick out the one that's actually the cheapest edge. And in this arbitrary first search, usually you start from some vertex, right? If you're trying to solve minimum spanning tree, there's not inherently a vertex that you want to start with, but you can just start with any vertex. I told you that actually the minimum spanning tree is always unique. So whatever solution you use to find it, you're always going to get the same thing. So it really doesn't matter where you start. So that's the algorithm. And while we're here, mainly I want to analyze why this gives you the minimum spanning tree correctly. But just while we're here on this slide, let's spend 2 seconds talking about how you would actually implement it. Now it's a bit more painful because you care to, every time you pull a tile out of the bag, to pull out the cheapest one, the one that has the lowest edge cost. So if you just use a stack or a queue, the edges are in there in some arbitrary order, and you might have to just look through all of them to find the cheapest edge. Okay, which is order of E time, if there's that many tiles in the bag, so maybe the overall running time is quadratic. And you know what, this is we mainly care about the distinction between polynomial time and exponential time in this class, so that's good enough for us for now. I will say though that if you're more sophisticated, and probably you'll study these things in 210 or something, you might use a data structure called a priority queue for this, or a heap, which kind of keeps the bag edges in some kind of semi-sorted order. There's a trade-off between the putting in and taking out. Like if you want to keep it totally sorted, then this step, taking out the cheapest edge, is very fast. But putting an edge in is very slow because you have to resort everything. So there's some kind of nice trade-off between those two things, and you can get it so that both the picking and the putting are logarithmic time. I won't say how. It takes a little while to explain. But anyway, you can do this algorithm in E log E time, M log M time, which is actually quite good. Okay, so let's actually now talk about the correctness, why this actually finds the minimum spanning tree. That's what we care about more. And just so that you don't have to remember all the 10 steps in the algorithm, basically what's going on with cheapest first search is you start with S, and you sort of slowly grow this spanning tree out from it. And the cheapest rule means that you always add the cheapest edge next, coming out of S. So if this is the example, you start from S. The cheapest edge coming out is this one, it's 5. The cheapest edge coming out of S and V now is this one. Now you have S, V, and B. The cheapest edge coming out of all of them is this one. Now the cheapest edge coming out of S, V, B, and T is a little bit hard to find, but it's actually this one for 12. The next one coming out that's cheapest is this one. K is the only one left, and the cheapest edge coming out going to K is this one. So that's how the algorithm works, and we're going to prove that this kind of sort of greedy algorithm actually finds the minimum spanning tree. Okay, so that's our theorem. And again, we're going to try to prove it by induction. So what we're going to really prove is that, n minus 1 edges get added in the end. We're going to prove that for each k, the first k edges all belong to the minimum spanning tree. Okay, and if we prove that for all k, then in particular it's true for k equals n minus 1. So in particular, the final thing we find, all of the edges are in the minimum spanning tree. Okay, so it's going to be an induction. So the base case is k equals 0. You want to claim that once 0 edges have been added by the algorithm, all 0 of those edges are in the minimum spanning tree. Well, it's a vacuous statement. There are no edges to talk about, so that's true. Okay, so let's do the induction step. So let's say you run this cheapest first search algorithm for a while, and you've added k edges. So there's k minus 1 vertices sort of in the tree you've built so far. And they're all in the minimum spanning tree by induction. And then what happens? You add the next edge. And what we want to show is that that next edge is also in the minimum spanning tree, which we don't know what it is. I mean, the algorithm is trying to find it, but nevertheless, as the analyzers of this algorithm, that's what we're trying to prove. Okay, so let S be big S be the set of vertices connected to little s so far. So maybe this is the picture. We started at S, we added like 3 edges, and capital S is this set of 4 vertices. And we're assuming by induction they're all in the minimum spanning tree. And we want to say whatever edges are added next, it must also be in the minimum spanning tree. So let's say E is we'll just give a name to it, is the edge added next. Let's say E connects V and W. So E is going to have one endpoint inside capital S and one endpoint outside capital S, right? I mean, as cheapest first search is going around, it might pull some other edges like that are cheaper, but they'll be internal to S. Like maybe it might pull this edge next because it's very cheap, but then it would say, oh, we've already visited V, so we can throw it out. Okay, so you keep going until it finds the cheapest edge that takes it to a vertex it hasn't seen yet. Okay, so by definition, E is the cheapest edge that like comes out of S, capital S. Okay, so let T be the minimum spanning tree for G, which again, the algorithm does not know what T is. It's trying to find T, but we, the analyzer of the algorithm, I mean, this is a legitimate math step to just say, well, it's something. Let's call it T. So I kind of hypothetically drew it here. So T is supposed to be the set of all yellow edges here. And let's assume, for the sake of contradiction, that E is not in T. Okay, but we want to show that E is actually in T, so let's assume that, hypothetically, it's not in T. Okay, so now we got to get a contradiction. And what will we probably be contradicting in the end? That it's not a minimum spanning tree. Yes. Somebody want to say what more specifically? It's more of a guess, but I mean, what is a minimum spanning tree? It has like 2 components. Yeah. Yeah. I mean, a minimum spanning tree is a spanning tree. That's the cheapest spanning tree. And we're going to be contradicting the second thing, that it's the cheapest spanning tree. Kind of have to, right? We already said that T, well, it's not clear, I guess, but we're going to be using the fact that T is a tree, but we're going to contradict that it's the cheapest. Because somehow it doesn't use E, and E looks like it might be a good edge to use, since it's the cheapest edge coming out of S. But it's not clear. Okay. So I guess the strategy is we're going to build a different tree, T prime, that's a spanning tree, and argue, and it's going to use E, and argue that it's cheaper than T, contradiction. So we kind of want to build a new spanning tree that uses E, and argue that it's cheaper. So probably we're going to try to put E into the spanning tree, T. We're going to have to take some edge out of, I mean, that will make a cycle, so we're going to have to take some edge out of T as well. So we have to figure out which edge to take out. And here's how we're going to do it. Since T is a spanning tree, all the vertices are connected by the edges of T, these yellow edges. So whatever V and W are, they're connected by some path in T. So let's follow that path from V until the first time it exits S. So there's a path from V to W. And let's say E prime is the first edge on this path that exits S. So there it is, and let's call its endpoints V prime and W prime. And that's actually going to be the edge we switch with. OK, so I'm going to move past this slide, which has a lot of information on it. Are there any questions? OK. Great, so I deleted this path, but T, or I didn't show it. But we have this edge E now, the cheapest edge coming out of S. And we have this other edge, E prime, which is a path that's in the supposed minimum spanning tree T. It's the first edge on the path in T from V to W. OK, and here's what we're going to do. We're going to take this T prime, which we get by adding E and taking away E prime. And we're going to claim that that's a minimum, that's a spanning tree. And suppose this is true. I mean, this is the hard part of the proof, to show that it's a spanning tree. Why can we get our contradiction then? Yeah?
Because since E has a lower weight than E prime, and then therefore you can always construct a minimum spanning tree that's even smaller than that. And then by the exchange theorem, you know that therefore that shouldn't be the minimum spanning tree. The one that we came up with isn't the minimum spanning tree, and therefore there's a contradiction.
Just your first sentence was the contradiction. I mean, I'm saying let's assume we could prove this, that T prime is really a spanning tree. Why do we get the contradiction? It's basically because E is cheaper than E prime, which is what you said. I mean, by assumption, by the algorithm, E is the cheapest edge coming out of S, this set capital S. E prime is some other edge coming out of capital S, so it's more expensive than E. In fact, it's strictly more expensive than E. That's where we use, this is the one spot where we use that the edge costs are distinct. OK? So the overall cost of this T prime we made, we took out a more expensive edge and put in a cheaper edge. So it's cheaper overall. All the other edges are the same. So it's cheaper than T. So if it's also a spanning tree, then we get a contradiction, because T prime would be the minimum spanning tree, not T. OK, so now we're just got to finish. It's going to fit on this slide. We've got to finish proving this claim that T prime is really a spanning tree. Well, it's a set of edges. That's a good start. And in fact, it has exactly cardinality of V minus 1 edges, right? Because T was a minimum spanning tree, so it was a spanning tree. So it was a tree on cardinality of V vertices. So T had V minus 1 edges. We took out one edge and put in another. So T prime has V minus 1 edges too. So the other thing we have to check is that T prime still connects all the vertices. OK, and at first it might look a little worrisome, because we took out this E prime from T. T connected all the vertices, but we took out this E prime. And that might have been crucial to connecting some pairs of vertices in T. But, luckily we put in E. You could say to yourself, suppose that we had a couple of vertices in the graph. They were connected in the original T. Now maybe that connection used this edge, E prime. And now we just deleted it, so we could be in trouble. But wherever that connection was, it maybe went from, let's say it was going from S, the top to the bottom. Went along here. Now I wanted to use this edge. It can't. But V prime is connected to V, because it was on the path from V to W that defined E prime. So we could just go back to V. Then we can go across E, which by assumption we're adding. And then W is also connected to W prime, because again, E prime was defined to be this path edge on the path from V to W. So we can go over to W prime, and now we're at W prime, and we can finish the old path, or the old walk. OK, so any old walk that used E prime, we can instead have it use E by going to V prime first, going back to V, crossing E, going to W prime, and coming back. OK, any questions about that? So it's actually the end of the proof, because it's the end of the proof that T prime is a spanning tree. T prime is cheaper than T, so T was not the minimum spanning tree after all. So we get the contradiction that E had to have been in T. OK, so that's it. And it shows that the cheapest first search algorithm, which you can implement somewhat efficiently, finds the minimum spanning tree. Now let me make a small observation here. Actually, I don't expect you to necessarily get this, but if you look back at that proof we just did, we actually didn't use the induction hypothesis. We didn't actually use that the edges we'd already found so far inside capital S were part of the minimum spanning tree. I don't know, we didn't. You can check. All we really used was that E was the cheapest edge coming out of this set of vertices S. So we actually proved a somewhat more general fact. Over the course of the proof, we proved this thing which is called the MST cut property, which says that suppose you have any graph with distinct edge costs, and S is any set of vertices. Well, S should have at least one vertex in S, and there should be at least one vertex not in S, but any set of vertices otherwise. And suppose you find the cheapest edge coming out of the set of vertices S. So the cheapest edge with one vertex in S and one vertex outside of S. Then the same proof we did shows that any minimum spanning tree has to contain this edge. So that's an important property of MSTs. And it's kind of nice because it's very comforting. Like you find some edge that's very cheap, and it goes from one set of vertices inside a set of vertices to outside of the set of vertices. You can always sort of like add it into an MST you're building. And as a kind of consequence, like you can sort of show that pretty much any natural greedy algorithm you might think of for finding the minimum spanning tree actually works. So there's actually several minimum spanning tree algorithms out there with names. One is called Kruskal's algorithm. It's from the late 50s. And it's simple. You sort the edges in order of cheapness, and you just go through them one by one, like cheapest to most expensive, and you sort of try to add it to a minimum spanning tree. You only don't add it if you don't need it, like if it would already connect two vertices you've connected. OK, and that's it. And it's not hard to show using the cut property that that will correctly find the minimum spanning tree. Every edge that it thinks to add must actually be in the minimum spanning tree. I can also tell you what Boruvka's algorithm was from 1926. This is a very nice algorithm if you want a parallelizable algorithm. You basically take the graph G, and you take away all the edges for a minute. And so you have n connected components, the little vertices. And then, in general, you look at each connected component you have so far, find the cheapest edge coming out of it, and you add all of those edges for every connected component that you have. So it sort of grows a bunch of trees in parallel, always adding the cheapest one out of each connected component until you've connected everything up. OK, so I didn't say that precisely, nor did I prove precisely that it works, but it all comes quite easily from this MST cut property. Any questions? OK, so we have 7 minutes left, and I will tell you a story. I can't rob you of this one. It's kind of a nice story. Suppose running time for MST algorithms. So there's sort of 3 or 4 classical algorithms from before 1960s. This Boruvka, this cheapest first search one that we studied due to Yarnik and Prim, this Kruskal one. They all run in time m log m if you are mildly careful about using a nice data structure. And that is very good, OK? It's practically linear time, except for this small log factor. If you run it in practice, it's fine. Nevertheless, the theoretical computer scientists were like, let's see if we can do it better, faster. So the first big improvement came like 20 years later due to Fredman and Tarjan. They invented a very tricky data structure called Fibonacci heap. It's quite tricky. I studied it in graduate school. It's not crazy, but it's tricky. But they got like an amazing kind of running time improvement. They improved it from m log m to this running time, m log star m. Now, I don't know if you remember from lecture 7 what log star m is. I will tell you. It's the number of times you need to log a number to get it down to 2. So like, if log star of a number n is k, that means n is roughly 2 to the 2 to the 2 to the 2 to the 2 k times. Okay, so I mean, repeated exponentiation is very large, so like its inverse, log star, is very, very, very slow. Okay, so for every like real world scenario, log star of m is at most 5, because that's like saying for every real world scenario, the number of edges is at most 2 to the 2 to the 16, which is definitely true, right? 2 to the whatever, 64 million. Okay, so in practice, this is basically 5. So you're like, okay, it's basically a linear time algorithm, but theoretically, it's not actually linear time. But that was pretty cool. Here's, okay, so this is Tarjan on the left. This is not Fredman. And this is actually also not Fredman. It's basically, I mean, I don't know if even Nancy Drew could find a photo of Fredman on the internet. You can try to find him. There's 2 other famous theoretical computer scientists. Okay, so a couple of years later, people were like very excited about this. And they're like, let's try to hack on it and make it even better. So this is Gabo, Galil, Spencer, Tom Spencer, and Tarjan again. They improved the algorithm. They got the running time down from m log star m down all the way to m times log of log star m. It's a little bit ridiculous. At this point, it's all kind of for jokes. Like m log star m is like super, fast. And these algorithms you would never run in practice because, I mean, this is already basically 5. So what are you doing? But, it's for like the math love of it. And, they invent new algorithmic ideas and new data structures. So, I mean, it has worth in that way. So, of course, this is at most log of 5 for all real-world purposes. And this is Gabo, Galil. It's also impossible to find a picture of Spencer online. So I showed Tarjan and Gary Johnson and Johnson's wife in this photo. Okay, now flash forward another like 10 years. A very famous computer scientist, Chazelle, invented a new data structure called soft heap. And he improved the running time from m log star m to m times alpha of m times log of alpha of m. So basically m times alpha of m. Okay, there's this little additional log alpha m factor, but basically m times alpha of m. I'll tell you what alpha m is in a second, but I assure you it's some comically slow-growing function, even slower, like smaller than log star. Well, that's Bernard Chazelle right there. So then a few years later, he got off that log alpha factor. So he got it down to this m times alpha of m. So what is alpha of m? It's called the inverse Ackermann function. Okay, so you know how log star is the number of times you need to do log to get down to 2? Well, still won't tell you what alpha of m is, but there's something called log star star m, which is the number of times you need to do log star to get down to 2, which is really ridiculous. And then there's log star 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 m, which is the number of times you need to do log star star to get down to 2, etc. But these things all grow super fast compared to alpha. Alpha is the number of stars you would need to put in so that log of that many stars of m gets down to 2. There's actually some other problem Tarjan figured out where the optimal running time is m times alpha of m, which he could prove, but it's not for this one. Well, maybe not. Actually, this is such a ridiculously slow-growing function that, for example, if you want to prove a theorem about this inverse Ackermann function, like you cannot use even piano arithmetic, if you remember what that was, to reason about it. Okay, so anyway, this is some ridiculous algorithm. Running time. Now, check this. Actually, in 1995, Karger, Klein, and Tarjan, again, actually gave a linear time algorithm. But there was a catch, which is that it was a randomized algorithm, yeah. And it was like the expected value of the running time was linear in m, order of m. Which is fine. We're going to talk about randomized algorithms here. There's nothing wrong with randomized algorithms. They're great. In fact, I mean, it's awesome because this algorithm is much simpler than Chazelle's algorithm and stuff. So that's quite good. That's Karger, Klein, and Tarjan again. One sec. Now here's this is my favorite part. So that's good. But people went back and were like, what if we really wanted a deterministic algorithm? I mean, there's no special reason for that, but since this is all kind of for jokes anyway, they gave a new deterministic minimum spanning tree algorithm. And they proved that its running time is optimal. Well, they proved that it's at most a constant factor worse than optimal. So that's awesome. That's it. That's the ultimate algorithm for MST, deterministic. There's Seth Petty and Vijaya Ramachandran. So, you want to know what the running time is? We also want to know what the running time is. It's a funny thing. Its running time is unknown. They prove that it's optimal, but they don't know how fast it is. So it's somewhere between order of m, which is a lower bound, and order of m alpha m. Whatever it is, it's optimal, but they don't know what it is. OK, see you on Thursday.